then Mr. Arsenault will be able to directly interact with you with these things. He's going to do the sequence
This is the closest I
series
can sit to the front in this
too.
room.
Okay. That's the best you can do.
No, it's not. Not even right now.
You do this. We're going to fight you in.
Wait, I can't sit. Oh, I'll sit here.
I guess it's there.
Is this yours? Packet? Your ID packet. Or should I
Oh,
just-
yeah, just leave them on there. Leave them on there. Weren't they down here?
Yeah.
Is that all right?
Yeah.
Just so that this is available.
I'll
Okay,
take some of
so
this.
guys, croissant, you can learn this in 30 seconds or less.
Yay. I like stuff like that.
Yeah, I like something.
Poison.
Okay, so I don't think it's a big deal. Yes, it's from Wikipedia. What I like, if I didn't draw a bracket on the lower left, would you please do that? I like this sheet because it spells out nicely what these things stand for. Okay? So, Poisson is the law of rare occurrences. So it actually was developed to like figure out the probability that your horse would lose a shoe in battle. That you would be at an intersection when a fire truck came through. They're rare occurrences. They don't happen that often. So it's designed to match this very unlikely thing that doesn't happen on a regular, predictable basis. E is who you think E is. K is the number of occurrences. K is what you're trying to figure out. So if you're trying to figure out the probability that a horse will lose a shoe twice in a year in battle, then K is what you're twice is K. Is that okay? Mm-hmm. That's what you're working for. That's what you're looking for. This is what you're solving for. But this is what you're solving for now. You couldn't use this function if you didn't know that in some 10-year period in the past, the horse lost the shoe 6 times. So they have to have some previous data, or you couldn't use Poisson. Is that okay? So they'll always give you some previous data. So that's obviously k factorial is what it is. The lambda describes the expected number of occurrences in a given interval. Okay? And Mr. Arsenault has an actual problem for you. So we're going to trade off back and forth from this side. Okay, so this is from the past. But you have to watch out for the number of occurrences in an interval because it may not match what you're looking at. Okay, but this is past data. So if you take a look at it, this is, I'm just setting it up and then Mr. Arsenault can take this right over. You're going to take the past occurrences, so if it was 6 times we said, and you're looking for the probability of 2, you're going to raise e to the minus 2, and you're going to put it over the, well, is it minus 2? Past 6, and then you're going to put it over k factorial, 2 factorial. So if you can just, the key to Poisson is simply memorize what they stand for. So lambda happened in the past, it's an old Greek letter, and k is current, and that's what you're looking for. If you can remember those, the formula is kind of like an APERT formula, so it has an E in it, and you just want to memorize it.
And then just some other, on this packet I gave you, I mean the test I gave you, it's more than just lambdas. I think only problem number 5 is the Poisson, where some of the other ones are binomial probability, which is also IB. So problem like number 4 is a binomial. Problem number 6 is sort of a variation on a binomial. I don't think the IB would go to that extent where they change probabilities depending on where you are, but that's just taking it to the next level with what I did in a different class. So 4 and 5 sort of relate to the these topics, and we can look at that. And then the expected value formula is part of it also.
You know, we need
problem 2, I forgot to put a diagram in. Since I just recopied this, I usually added a new diagram each time, cumulative distribution function. But
you know what we mean by binomial, like 1/6 times 5/6, 1/6 to 1, you know, like a true-false test.
binomial.
That's sort of your multiple choice.
True, yes, true plus false, or yeah, probability of success plus failure always adds up to.
We don't want to scare you with that. You've done those.
Yeah.
They're algebra. Here, they're algebra 2. They're
Binomial is just this: the probability of success plus probability of failure to the n power. So if you flip a coin, and it was a bias coin or something like that, 3/4, 1/4. What's the probability of getting 4 heads? It would just be, if you flipped it 6 times, 6 choose 4, 3/4 to the 4th, and 1/4 to the 2nd. So it was a bias coin. But that's a binomial distribution, so it's always just it's the binomial theorem expanded, and usually you're asked for one part or another. So that's what problem number 4 would allow you to do, is practice different things like that. And then part C of that, and we'll talk about that one as well, conditional probability, given that something's, that something's happened, because that's one of the formulas on the IB packet also. Okay, yeah, one other thing just to tie this back into what we did in calculus. Now, this is the binomial probability for a specific event happening k times. So k can actually go from 0 to infinity. So if you think about it, we've got lambda k e to the negative lambda over k factorial. So k is our variable, so what can you say about e to the negative lambda? And it's also, k is our variable, e to the negative lambda is a constant. What's that series?
Oh, we got lots of.
Yeah. What series is that? You had 1 plus lambda squared over 2 factorial plus lambda cubed over 3 factorial. All right, that's e to the lambda. So remembering our series from last year.
Please remember all of them.
Okay. This is just showing you where Poisson actually comes from. They give you this formula. This is e to the lambda, and it's times e to the negative lambda, and you get e to the 0, which is 1. The probabilities have to add up to 1. If you go through all the different things that could happen, they always have to add up to 1. So that's showing you where Poisson came from. And what Poisson actually is a way to approximate binomial probabilities. So you could do the binomial problems using Poisson, and those would be approximations. And usually Poisson is used where this lambda is equal to n times p, when n is large and p is relatively small. That's why we use that. We wouldn't want to use a binomial probability to approximate what's the probability that you have an error in a book. If the probability of an error on a given page is like 0.0001, and there's 300 pages in the book, binomial wouldn't be a good way to do that. And Poisson approximates a binomial. Yeah, so that's where that comes from. Who needs this packet? You need that one. 2, 3, 4, 5, 6. So we're just missing.
Nithya's videoing on the computer speaker.
Oh, okay. Here's your test.
She can see you from there right now?
No. She's recording it.
Oh, recording it. Okay. Yeah, so that's where Poisson comes from, to give you a little history of what we've done before. It's just a way to approximate a binomial. And I don't know if you can see that, but that's the